Good morning, class. I'm just getting things set up and we'll start in a few seconds. All right, then let's get going. Um, we should, yeah, so we had some issues with getting the YouTube streaming to work, but that's fixed now. So things are back on track. All right. Just we are in the middle of the semester. We are the this uh, we are talking about we are getting into the thick of things now. So I just have one reminder slash announcement for you, which is about homework 4 that's available on Canvas. It's due day after tomorrow. And if you haven't yet started working on it, please do so. So, and it's essentially talking about stuff we did in the learning theory part of the class. So are there any questions about the homework or things like projects and such things? In question 4 on decision list, this is the extra credit question. What is the complement of a concept C? Could I give an example? Essentially, it's just a negation. So if I have basically it's the negation. So if I have something like, let me just pull up the homework so that I can use any examples that are in it if there's. By the way, the homework for question 4 is um, it's the extra credit question, and it's it's a pretty neat question. And if you do have time and want to think about it, I encourage you to. Um, so the complement, as the question says, is simply the negation. For instance, if you have a decision list, let me um, say, okay, so let's say I create this example using a certain decision list. It checks for X1, and then um, if X1 is true, by definition, the output goes to the side, and let's say it is a 0. Then you check for, say, X2. If that is true, then the output's a 1. Otherwise, let's say the output's a 0. So this is a decision list. And let's say this is 1, 0, something like that. It doesn't have to be um, just a variable here. It could be not X2, for instance. Now, let me describe what the complement of this is using by brute forcing it. I can think of this function as this tree as representing a certain truth table. So let's draw the entire truth table. Thankfully, there are only 2 variables, so I can check. So if let's look at one example at a time. So when X1 is 0, we have to go down the tree. Then we check for, so in this row here, then we check for not X2. Is X2 false? Yes. So this is a 1. The next one, X1 is 0. So we go down the tree. Then we check for not X2. It's true. So this is not X2 is false. So this goes away. Um, then the last 2 ones, you check for X1. Is it true? Yes. So it's a 0. It's a 0. This is the function. Now, the complement of this function, which I'm going to, let's call this C. The complement of this is not C, which is 0, 1, 0, 0, 1, 1, 1. And what the question is saying is, if a certain function can be represented as a decision list, then you can show, the question is asking you to show a K decision list that also represents its complement. And there's a big hint there. Instead of just proving, so there are, in general, there are many different ways of showing that something exists. One way, which is a constructive way, is to show by creating the object that needs to be shown. So essentially what the question is asking you is, given a decision list of this kind here, take this and convert it into a different decision list, a K decision list that expresses this concept. Does that answer your question, Han? So there's another question. What does it mean by closed form expression 1.1.d? What that means is it cannot use any s n of I minus 1 and so on. So it's just, it should be an expression purely in terms of n, k, and any constants, but not any of the capital S terms. So let's see. Okay, there are many questions suddenly. Can you show the steps from step 1 to step 2 on slide 41? How does the inequality flip around? This is I think I know where. Yes. This is actually a rather technical discussion. So I'm going to postpone this for Anthony. I'm going to postpone this for later. But the short answer here is notice that the definition of M in these two slides, in these two expressions, is slightly different. The first one says, if you have at least M examples, then everything that follows is true. The second one says, if you have more than M examples, then basically the M in the first step and the M in the second step are slightly different. M is in the second step is the minimum number of examples that are needed for a certain kind of training error. We can take this discussion offline because I don't want to get into a rather nuanced and somewhat, at least for the scope of this, what we are doing, somewhat unnecessary tangent. So in fact, just to kind of wrap that up, if you can't make it to Office Hours, send me a message. I can point you to a certain chapter in one of the textbooks that are recommended for the class, which is available online, that discusses exactly that point. So I can point you there also. So another question: can you briefly explain about sample and time complexity? And I don't know if it's a follow-up, but in question 1.3, should we consider a fixed number for K? So the first one is easy. Second one's easy. For question 1.3, yes, do consider K to be fixed, K to be a small fixed number. It's not a complexity parameter. It's not something that it depends on N, for example. For question 4, in fact, when I say that the number of features is large, for the sake of discussion, you can even assume that what happens. Okay, you can even consider the case when K is really, say, some linear function of N, not some function of N. Okay, but going back to your first question, what's the difference between sample complexity and time complexity? So sample complexity is a property of the task. Sample complexity is asking, so sample complexity is asking, how many examples do you need to learn a certain concept? So this is really number of examples. Time complexity. So this is, let me just write this down. Sample complexity is going back to sample complexity for concept C. Time complexity is number of steps an algorithm take in worst case. So we can think about this in two ways. Time complexity could be for a concept C and an algorithm A, which we are asking what's the time complexity of a certain algorithm, or we can think about the complexity of just the concept, which in which case it's the worst case. Um, does there exist, if we are asking questions about time complexity, is there an algorithm A that has polynomial time complexity and so on? So the time complexity is always about, think about running time. And sample complexity is purely about the amount of information that's inside a certain number of examples for a particular concept. Sample complexity is an information theoretic notion, if you want to go that way. A time complexity is a computational notion. It talks about how much time will an algorithm take. Related to question 1, part 3, um, again, it's the same question. How can we get uh, a bound for the computation time? There's no formula for this in this thing. Yes, we did not discuss a formula for this. In fact, I would like you to think about how you could do it by thinking about um, this question. Is there an algorithm that that allows you to understand the number of steps needed? Um, I'm deliberately not talking about that in the class because that is really something that I assume you have seen somewhere, hopefully, in some sort of a discrete math class or an algorithms class somewhere, about how to compute the number of steps needed. We did not explicitly cover that. I would argue that's something that hopefully is part of the prerequisites. However, if you have any questions about that, please come to office hours. We can chat about that. So, so there's another question. I understand the computational complexity requirements of an algorithm for path learnability, but what are the requirements on the accuracy related to the data? Um, so I can produce an algorithm that produces a tree, but what's the requirement on the type of tree that the algorithm produces? That is how accurate. So this is interesting. So the question really asking, and correct me if I'm wrong, Ben, is the question's asking if I can always create a tree that works on the data. But what can I say about its accuracy in the future? The answer is you can't. Because this is an interesting and important point. So let me kind of revisit this briefly because it may have slipped through. So let's take a certain algorithm. Sorry, let's take a certain concept class C for which we have some data set with M examples. Now, think about what all the pack bounds that we've encountered are saying. They're not talking about how accurate a classifier is. All we are asking is what is the general. So in the consistent case, we are asking, does there so I'm not going to write the whole thing. So in the consistent case, what we are asking is, does there exist a certain hypothesis that is bad? We're not asking about the best hypothesis at any point. We're just asking, does there exist some hypothesis that's bad? Because if there exists even one hypothesis that's bad, what does bad mean? Going back to the proof of that particular, the first, the theorem that we saw, the Occam's razor. We define bad to be a classifier that is perfect on a training set and yet has high generalization error. And the entire theorem was, the proof of the theorem was asking, what's the probability that exists some hypothesis that's bad? And we're not ever claiming that the learning algorithm will choose the bad hypothesis. It's entirely possible that the learning algorithm knows to avoid it. But since that entire theory is built independent of any particular algorithm, we are even considering the case where the learning algorithm chooses a rather lousy classifier. And we want to bound the probability that even that cannot happen. So what that means is if for that particular example with the consistent classifiers, even if the classifier is consistent with the m examples, there's a probability that it will be bad, and we want to bound that bad in terms of accuracy. In the case of the agnostic setting, once again, we are not asking about, at no point do we assume that the learning algorithm somehow finds the best classifier. In the case of agnostic learning, all we care for is the gap between the training error and the generalization error. And we're asking, does there exist some classifier for which the gap between the training error and the generalization error is really large? And if that happens, we will, there's a possibility that some learning algorithm, we don't know, since we are not at that point, we're still not thinking about any particular algorithm. There's a possibility that some learning algorithm might end up choosing that bad hypothesis. So we want to reduce that probability. What I'm getting at is, at no point are we making an assumption that our learning algorithm chooses the best classifier in a training set, because we are making a statement about any classifier that the learning algorithm chooses from the training set. What's the probability that its accuracy will be, its generalization accuracy will be really bad? So because if you want a reminder of where this shows up, in all cases, we had some probability that some hypothesis in the hypothesis space is bad, is equal to some expression. And from there, we use the union bound to say probability that there exists some hypothesis in H such that H is bad. When we did that, we are essentially saying this algorithm might just pick anything randomly. So the going back to the thing, so to kind of follow up with your clarification, the algorithm, it does not have to produce something that's consistent with the training data. For the pack bounds to show up, the algorithm might even produce some classifier that is any classifier that is uh, um, that has low error, that has some error. So if we are in the agnostic setting, it produces some classifier. And the theory that we are building says how much worse will it be at test time. Remember, for agnostic learning, the guarantee, the epsilon for agnostic learning, is how much worse will it be at test time. For the consistent case, the epsilon is how much, what's the accuracy of, what's the error of the classifier. So we talk about epsilon. There are two meanings here. In the consistent case, we have it's the error. In the agnostic case, it is the gap, the in some sense, error D minus error S. In this case, it's just error D because error S equals 0. So essentially, these two terms are the same, but it's always how much worse will it get at test time. So the algorithm might produce, the algorithm is allowed some slack on the training set. If it's allowed some slack on the training set, this term will no longer be 0, so you'll be in the agnostic case. If it is always guaranteed to produce a 0 training error, then you'll be in the consistent case. This kind of, I went around a few different things, but kind of very briefly to wrap up that point so that I don't spend the entire class just talking about one question. When we built up the theory for pack learning, we didn't assume that we didn't really care about low error on the training set. What we cared about is how much worse can it get in generalization. So that is the epsilon. So the epsilon during that we care about is always, can it get much worse in the future than it was during training? And that is the epsilon that shows up in the pack bounds, and that's this gap here. I hope I've given you a hint, Ben, about what you were asking. How do we determine what low error is? We don't. It depends on the application. It's just Assume for now that epsilon is given to you by someone who cares about the problem. So you're given some definition of what is low. So you're given an epsilon, and all you need is that the computational complexity should be at most polynomial in epsilon, 1 over epsilon, maybe even independent of 1 over epsilon. Let me go back to the questions related to problem 3.3c. This is the VC dimension question. Yes. Could you give an example of what a finite class of functions could look like? Sure. All Boolean functions that we considered are finite class of functions. Any function that say is that where the number of concepts that exist is only polynomial is finite. Sorry, not polynomial, is finite, is defined to be the finite class of functions. So an infinite class of functions would be defined using some real numbers, for instance. A finite class of functions would be defined. So we've looked at many different finite function classes. So decision trees are finite. All Boolean functions that we consider are finite. Infinite classes include things like linear classifiers. I think the one that we've studied in a fair amount of detail includes is linear classifier, but there are others. We saw some examples of infinite classes of functions like those rectangles that we were drawing, or the axis aligned rectangles and such things. So basically anything that where the number of functions is not infinite. For question 3.3a, can we explain how to obtain the VC dimension for a finite hypothesis class based on the number of, this is a good question. This is a question for which let me show you an example rather than, this is an example I think that someone asked me in office hours also. So let's say that I have a finite set of functions. And again, this is also maybe a clarification for Hunter's question. So let's say I have a finite set of functions. Let's say I have exactly 4 functions. I have only 4 functions. My entire set of functions that I'm going to consider for learning is these 4 things. I don't care what data set I get. I'm going to pick one of these 4 things. This is a toy problem, of course. Now, let's think about what it means to shatter for shatter some set. Let's say I have a set of instead of 4, let's say I have 8. Let's say I have a set of three examples: x1, x2, and x3. The definition of a VC dimension is given some 3 examples. In this case, we are asking, is the VC dimension of this at least 3? So to do that, I need to consider every, or actually, let's take just 2 because I'll run out of space. To do that, I have to ask, consider every possible labeling of these 2 examples. x1, x2 could be, x1 could be labeled plus, and this could be labeled plus, minus plus, plus minus, and minus minus. These are the only 4 ways in which these 2 examples can be labeled. And for the VC dimension of C to be at least 2, the question we can ask is it possible, we don't know what these functions are, but is it possible that some assignment of these functions could satisfy this exact labeling? Or let me ask the inverse question. Is it impossible for any definitions of these functions to provide these labelings? And the answer, of course, it's entirely possible that maybe f1 works here, f3 works here, f6 here, and f8 here. It's possible. Nothing prevents this from happening. Maybe the definition of the functions prevent it, but there exists some set of definitions for these functions such that f1, when applied to x1 and x2, would assign plus for x1 and plus for x2. f6 would assign a plus for x1 but a minus for x2. It's entirely possible. So the VC, this does not prove that VC dimension is more than 2. This is just saying the VC could be greater than or equal to 2. So hopefully this is a hint. I want you to kind of keep working with this and, think about, okay, could the VC dimension be more than 3? Could the VC dimension be more than 4? To make your life, to kind of get a sense of how to proceed with this, work through the example in full detail. Work through this example, write it out in all, by assigning all possible labelings, and think about uh, uh, whether you run out of functions at some point. There are no longer more functions to kind of work with anymore once you get to a certain point, and then there's something interesting. Last question for epsilon. How come none of the slides directly show that epsilon equals error d minus error s? Actually, they do, if I remember right. So in yes, they actually do at some point in yes. So in slide 28, it says that the training error that's bounded by epsilon away from the true bound. So when we talk about Heffding's inequality, that's actually exactly what we're, in fact, slide 27 also talks about that. The error D is greater than error S plus epsilon. So we are always asking what's the probability that error D greater than error S plus epsilon. And that's exactly what it is. Yeah, it's not an equality. The epsilon is a bound on this. So epsilon is then less than D minus, oh, did I say some? So basically we are asking how much worse can it be? What's the probability that epsilon is, we want this probability to be low. So we want this to be less than delta, which means this situation does not happen. As a result, error D is going to be less than. If this is a rare, if this delta is small, then this event is rare, which means it is more likely that error D is less than error S plus epsilon. As a result, the generalization error is not more than epsilon away from what we see during training. Cool. I'm going to now switch gears. It's been about half an hour since the class started, and we're still talking about homework. If there are more homework questions, please come to office hours, and we'll continue on this. So I will now move to where we left things off with support vector machines. In the last lecture on Thursday, we looked at this idea of support vector machines, and we saw the story was when we have a low VC dimension, learning theory tells us that it leads to better generalization. And there was a theorem from Wapnick that said for linear classifiers, the VC dimension is inversely dependent on the margin, which means if you have smaller margins, you have better generalization. Using this idea, we designed a way to learn linear classifiers that did I say smaller? If you have a larger margin, you have better generalization. So using this idea, we decided to build an approach for training a linear classifier that says, if your data set is perfectly separable, there may be many, if your data set is separable of this kind, there may be many lines that separate out the pluses and the minuses. Among all of these, choose the one that has the highest margin. So prefer this instead of the blue line. So prefer this. Instead of so now this sets up a well-defined problem, but then it requires some massaging of the problem to get to a point where we can actually frame it as an optimization problem. There, that we saw looked something like this idea here. In order to find this maximum margin hyperplane, what we do is we solve an equivalent quadratic programming problem. In other words, we minimize the norm of the weight, minimize W transpose W, such that for every example, YW transpose X is at least 1. Now, this seemed like we've solved everything, but there was a big caveat here. This only worked for the separable case. So then we need to generalize this. The intuition for generalizing this was essentially to say, maybe we allow some examples to break into the margin. We do want to maximize the margin in as much as we can, but if there's an example that is just not going to work, we're going to pretend that it doesn't exist. And moreover, we are even going to allow some examples to break into the margin, because if you can ignore them, then you get a larger margin, and that's a good thing. This this approach took us through a few steps to a certain optimization problem that looked something like this. The way we do that is by introducing a slack variable, one slack variable for each example, xi I, for every example xi comma yi. For example xi yi, we introduce a slack variable, and the slack variable says, instead of putting the example such that yw transpose x is greater than 1, we want it to be greater than 1 minus the slack. So don't make it more than 1. Don't bother putting it introducing that gap of 1 step, 1 unit between the hyperplane and that example. Let it be 1 minus epsilon, 1 minus slack, 1 minus psi I. And this will allow you to essentially ignore those examples when we are computing the margin. So that gave us an optimization problem that looked like this. So we minimize, I'll highlight the things that were there in the original. So in the separable case, we were trying to minimize the norm of W transpose W. The reason we do that is this corresponds to maximizing the margin, provided YW transpose X is greater than 1. Now we have slack variables by saying, yeah, maybe for the ith example, I'm going to give this luxury of, for that example, to violate the constraint by this amount xi I, some positive number. So xi I should be greater than 0. But I don't want to give this luxury to all examples. I don't want to allow every example to just break the margin constraint. So I'm going to add this extra term here that says don't control the total amount of slack that's allowed. So this gives us a new optimization problem. We are minimizing now over W and xi, all the xi's. This norm of W transpose W plus C here is just a trade-off parameter which says which of these two terms is important. C times the sum of the slacks. We perform this minimization subject to two constraints, these two constraints here. The first one says, for every example, YW transpose X, this is the score assigned to that example, should be at least 1 minus the slack, and the slacks themselves are always positive. Now, this problem here is by itself completely well defined, and at this point, you can invent learning algorithms that actually just directly solve this problem. In fact, this was the way this approach for directly solving this problem was the way in which SVMs were optimized till like the late 90s, even mid 2000s. But it turns out that this particular problem is kind of slightly annoying, because you have to deal with all these constraints and all these things. So there's another way to kind of essentially construct an equivalent problem whose solution will be the same as this, and it will not have any of these slacks. So let me very briefly introduce this. We can eliminate the slacks by noting, by combining these two equations, these two inequalities, yi W transpose xi is greater than or equal to 1 minus the slack I. I'm going to move these terms around. This goes here, and this goes here. So the slack is greater than or equal to 1 minus YW transpose X. And we also know that the slack is greater than or equal to 0 from this constraint here. So we have the slack that's greater than 1 minus YW transpose X, and it's also greater than 0, which means the slack is greater than or equal to the max of 0, 1 minus YI W transpose X. I can just make it it's slightly more compact. Okay, so notice that the slack is always going to be greater than that. And because we have a minimization problem, we can essentially construct a bound for this objective by plugging in this expression here. Solving the minimization problem, once we plug it in, the objective will no longer have the slacks, so we can essentially ignore them. So what we'll get is this shows up here, and we have this max of 1 minus y w transpose x showing up instead of this thing here, and the c of course remains. But because we don't have any psi i's anymore, we don't have any more constraints. So these two forms of the optimization problems are equivalent. Now, now let's I have just taken one equation, done some algebra, and rewritten it in a different way. It turns out this expression is actually pretty cool because it is much more interpretable. And let me show you some a way to think about this expression. But before that, I would like to pause for questions because this was also a time for you to think about questions from last week, for example. Is C given? C is a hyperparameter. We've introduced our new hyperparameter for SVMs. In fact, this kind of a hyperparameter is going to show up pretty much for all learning algorithms going ahead. This I'm calling it a trade-off, and I'll show you why it's what trade-off it does. In fact, that's the interpretable thing that we'll get out of this second representation. So let me go there, and while you're thinking of questions. So the way to think about this is the first term is talking about maximizing the margin. This just came from before. And the second term can be interpreted as a penalty for that the weight W has to face for making the prediction for whatever prediction it makes on this example, given that the ground truth is yi. Let's see why. Let's take 3 cases. Let's kind of work with the thing in the box and consider 3 cases. So the first case is if the example is classified correctly and it's outside the margin. What that means is if the example is classified correctly, that means yi w transpose xi is greater than 0, greater than equal to 0. This is the thing that we have seen for all linear classifiers for any scoring function. If you have a score of w transpose x, if it's positive and yi is positive, this product is positive. If w transpose x is negative and yi is negative, this product is negative. So that's fine. But it says here the example is correctly classified and is outside the margin. What that means is it's not just greater than 0, it's greater than 1. In this case, 1 minus yi w transpose xi, this means is less than 0. Yi is the ground truth. So we are given an example xi with label yi. So 1 minus yi, so this can either be plus or minus 1. So for any training example, if y w transpose x is greater than 0, then it's correctly classified. But we are considering the case where we have some weight vector w, which not only places y w transpose x to be greater than 0, but makes it greater than 1. That means 1 minus y w transpose x is negative, which means the max of a negative number and 0 is of course 0. The penalty for this particular case is 0, which is a totally reasonable thing. The example is correctly classified, and not only is it correctly classified, it's placed on the correct side of the margin. There's no need to penalize the weights. Imagine that we are, in all cases, we are penalizing the weights. We are penalizing this classifier. There's no need to penalize this classifier because it made a correct choice and also introduced this margin. Let's consider another case. When the example is incorrectly classified, the example is incorrectly classified, that means y I w transpose xi is less than 0, right? If it's less than 0, that means 1 minus, that means this means that minus yi w transpose xi is greater than 0. That means 1 minus that quantity is greater than 1. It's positive. That's all we care about, which means this expression here is going to be more than 0. 1 minus the max of 0 and that thing is the 1 minus yw transpose x. So if an example is incorrectly classified, then that particular weight w has to pay a penalty of 1 minus yw transpose x. Think of it as the price it pays for misclassifying that example. The third option is the example is correctly classified, but within the margin. So that means yi w transpose xi is greater than 0, but it's less than 1. But because it's less than 1, we can now, that means 1 minus yi w transpose xi is less than 0. This expression here is negative, which means, oh, sorry, this, I made a mistake here. That means 1 minus yw transpose x is positive. I just moved this here and swapped sides. Now, because this expression is positive, the max is going to be whatever that expression is, because it's the max of 0 and a positive number. So what that means is an example that's correctly classified, but asked to be inside the margin, also pays a penalty that's equal to 1 minus yw transpose x. So essentially what's happening is in the three cases that we are considering, so let's go back to that picture that motivated this whole discussion. If you have these three cases, if you have examples here, this particular, essentially the way to think about that thing in the box is how much, what should be the price that this particular line pays in order to make these predictions that we are seeing. On examples here, all these examples are correctly classified. Let's say this is positive and away from the margin. So it pays no penalty on this. On all these examples also, so penalty equals 0. Here also penalty equals 0. On this example here, it pays, the example is incorrectly classified. Ideally, it should have been on this side. So this is the negative side, but it's not. So the penalty it pays is 1 minus yw transpose x, which the geometric intuition for that is whatever this distance is. So let me remove some of the marks here. So the penalty that it pays on this example, on the negative example, is whatever that distance is. This is 1 minus yi w transpose xi. And on the positive example, look, this example has broken into the margin, and this quantity is again 1 minus yi w transpose xi. That's the penalty it pays. So the price of admission for choosing this particular weight vector is whatever this gap is plus whatever this gap is. And that's the penalty that the classifier has to pay. There's a question, why does the margin have to be 1? If it's not 1, you can always divide by whatever that number is and make it 1. So 1 is perfectly good thing to keep with, because you can divide by some constant and let the constant be absorbed into the weight. So we have these three situations. When the example is correctly classified, the penalty is 0. When the example is incorrectly classified, the penalty is 1 minus yw transpose x. And even if the example is correctly classified but placed within the margin, penalty is still 1 minus yw transpose x. This kind of a penalty is called the Hinge loss function. In general, this is called a loss function. We've already seen a loss function. When we talked about regression, we saw this loss function called the squared loss. For classification, we have encountered the first of our many loss functions that we'll see. Hopefully, we'll see actually at least one more very soon. This particular loss function is called the Hinge loss, and it takes the form, in general, all loss functions are functions of the ground truth for an example and a classifier. Essentially, the loss function is asking how much should this particular classifier pay on an example x that has the ground truth y. And the Hinge loss says the payment should be the penalty for this, whatever prediction it makes, should be 1 minus y w transpose x. There's a question, where do we divide by that number? You don't divide this objective by that number. You essentially deal with it when we talked about this particular situation. Let me pull up that slide that is heavily annotated, something here. This C ends up being that number. So we can set this functional margin of the closest point to be 1, because if it was any other number, you can absorb it into the weights and you would have an equivalent set of weights, which is the one that you would search over. Going back to the Hinge loss function. So the Hinge loss function, let me revisit this notion of losses, because this is an important concept. By the way, the C is not the same. That C was just a temporary variable that I used. So this loss is an important concept here. So let me give you a pictorial example. On the horizontal axis, I have this quantity yw transpose x. On the vertical axis, I have the penalty for misclassification. This is, imagine that we are thinking of a particular example, x comma y, and we are asking, what should be the penalty for a linear classifier that's defined by W? The red line here defines the ideal case. It's called the 0-1 loss. And the black line defines the Hinge loss. The 0-1 loss is actually the error. So remember, yw transpose x should always be positive. That means the prediction is correct. So what we are saying is that the 0-1 loss, if the prediction is correct, there's no penalty. There's no loss if the sign of y and w transpose x is the same. If the prediction is wrong, if they have opposite signs, then you lose 1 point. This is, you can think of this as how many points get lost when you make a misclassification. If you add up the 0-1 losses, you essentially get the total number of errors. So the Hinge loss is this step function that steps down at 0 to become 0 here, and then it becomes 1 whenever yw transpose x is negative. In an ideal world, if you want to minimize the number of errors that a classifier makes, the right thing to minimize is exactly this step function, because I want to find a set of weights that puts all the examples on this side, because that's where for every remember, this plot is for a particular example and a set of weights, and we want to find a set of weights that puts all examples on the right side, so that the total number of points that get taken away from it is 0. And every time we get an example where yw transpose x maybe is here, you lose a point. This is the interpretation of the 0-1 loss. The 0-1 loss is the ideal thing we would like to minimize if life was good. Unfortunately, the 0-1 loss is also, if you know, as you notice, not even a continuous function. At this point here, it's there's a jump. So it's not a continuous function, so that presents problems from optimization point of view. Another way of thinking about it is optimizing for minimizing the 0-1 loss is a computationally intractable problem. As a result, we need to invent surrogates for this step function that capture a similar intuition. And the Hinge loss is the first of many such surrogates that we will encounter. So what the Hinge loss says is, in this yw transpose x space, if an example lies here, if yw transpose x is more than 1, there's no penalty. If the if the label for a positive example is 1, then yw transpose x will be more than 1. If a label for a negative example is to be -1, yw transpose x should be less than -1. In either case, there's no penalty, because that example is placed not only is it classified correctly, but also it's classified it's placed far away from the margin. Incorrect classifications, namely when yw transpose x is less than 0, incur a penalty that keeps growing as you get more and more incorrect. As you get farther and farther away from the margin on the wrong side, this penalty increases. So for an example that's very close to the margin but on the wrong side, penalty would be somewhere here. For an example that's really far away, the penalty would be somewhere here. The interesting part about hinge loss is this little triangle in the middle. In that region, the classifier is the 0, 1 loss has a no error. Essentially, it's saying, yeah, YW transpose X is positive. We're good. However, what the hinge loss says, yeah, this is not good enough. Not only do I want the examples to be correctly classified, I want them to be on the correct side of the margin. I want them to be far away from not just the decision boundary, but also from this gap that I want to leave. And any example that lies in between is given a penalty that's equal to YW transpose X. So notice that the penalty decreases as you get closer and closer to this margin 1. And at that point, the penalty flattens out to be 0. This notion, this idea of the hinge loss is what builds the SVM objective. So this objective function is the SVM objective function. Now let's talk about this expression C. There are two different terms that the C is balancing. On one hand, if let's consider the case, actually, let's get there in a minute. Are there any questions about these interpretations of the hinge loss? So we started off with just the notion of maximizing the margin. It was this abstract idea. I just need to maximize the margin because we need the VC dimension to be as small as necessary, because that gives you better generalization. And where we ended up with is this particular optimization problem, which forms the basis of the support vector machines. There's a question. This is all well and good, and this is a valid question, Anthony, so I'm going to spend a bit of time on this. This is all well and good, but max is still not differentiable. This picture makes it very clear. Let me go to a cleaner version of this picture. At this point, that function is not differentiable. That's perfectly valid. In fact, that's the next thing that we will encounter once we talk about optimization. It turns out that we need to go beyond what we encounter in calculus for gradients. We need to think about this idea called subgradients, which applies for functions where of this kind, where there are only a finite number of non-differentiable points. And the hinge loss is actually a subgradient function. So there's another suggestion that's implicit in the question. Should we be using some other? Who said that if the goal is to approximate this function here, why are we settling ourselves with this function that is still not differentiable? Can we invent other surrogates? And that's perfectly reasonable. Right after we finish SVMs, we will look at a whole bunch of surrogates. In fact, we will see that the perceptron actually also fits in this picture. There's a certain loss that the perceptron minimizes. There's a certain loss that logistic regression minimizes, and different learning algorithms. In fact, another way of thinking about learning, there are certain machine learning books that introduce learning this way. The goal is to not approximate functions or anything, but the goal is to write down a certain loss function that we want to optimize and optimize that. And that's the notion that machine learning is essentially applied optimization. So you're perfectly right. Hinge loss is not differentiable at that corner, but it turns out it's not going to matter. So in fact, what we have seen here is a general learning principle. This is the learning principle that drives pretty much all of machine learning today. Well, not that's a very that's not a valid statement. It's a dominant principle in machine learning today that has seen wide utility. Let's put it that way. The notion is this notion of risk minimization. What we do is we define some definition of loss as a function of the hypothesis. So we are going to define loss of some hypothesis and the training set, given a training set. And the goal of learning is to find that hypothesis H that minimizes the loss. So once again, we are searching over all possible hypotheses to find the one that has the lowest loss. The perfect loss function from that picture is the 0, 1 loss. The 0, 1 loss is exactly the error. If you care about error and that's the only thing you care about, the right thing to be minimizing is the 0, 1 loss, which is that step function. Unfortunately, it is intractable to optimize that function. So we need to invent different kinds of surrogates that approximate the 0, 1 loss. That's a different, this is the slightly different principle or perspective on learning in general. The goal of learning is to minimize some sort of a loss function. And in the event that we end up with a loss function that is hard to optimize, we invent surrogates that approximate it as well as we can. Under this principle, but this is not enough, because we might end up with a classifier that gets 0 loss. Remember, this is minimizing the loss, basically misclassifications, if you want to think about that, on the training set. And this can lead to overfitting. We can get a classifier that's perfect on the training set, but not good enough in the future. The goal of learning is never never to be tested on the training set. We need to generalize on future. That's why we introduce this. There's this notion of regularization. A regularizer is a function, is a term that penalizes complexity. It penalizes over complex hypothesis, and we want to this is a design choice. We define different kinds of regularizers, and we penalize complexity in different ways. And this is essentially capacity control. So we don't want hypothesis spaces even that are too complex, that are too expressive. So we want to limit the expressive capacity. So regularization is a term that penalizes complexity. And then we also have the notion of loss over the training data. So this gives us this notion of regularized risk minimization. We want to find a classifier that has the lowest sum of the regularizer and the training loss. This may seem way too abstract. So let me ground it back to the SVM example that we saw. In the SVM, we had these two terms. We had this first term, which is completely independent of the training data. It's a term that says that essentially promotes larger margins. Why does it promote larger margins? Because we know that when the larger margin is larger, the VC dimension is lower, and as a result, we get better generalization. So simply minimizing this term would give us better generalization. And this term here, the norm of W squared, or the squared norm of W, or W transpose W, is called the squared norm regularizer, called the L2 regularizer. It turns out there are other regularizers which impose other kinds of preferences. This is a popular one. In fact, this is perhaps the most commonly used one. The L2 regularizer just says, among all hypotheses, I want the one that has the largest margin. There's this other term here, this expression, which is it's called the empirical loss. It's the loss on the training set. In this case, we are using the Hinge loss, and it penalizes weight vectors for making mistakes on the training data. So, and this also can be replaced by other loss functions which impose other kinds of preferences. The Hinge loss imposes preferences in the way that we encountered before. So we have these two terms. We are minimizing the sum of the regularizer and the empirical loss. Now, finally, to answer the question, I think that was asked by Han a while back, what about the C? The C is a hyperparameter that controls that gives you a trade-off between a really large margin, which is essentially saying this term gets very, very small, or a really large, really low training loss, a small Hinge loss. Now, this is a trade-off. Let's think about the extremes to understand how this trade-off works. Let's consider the case when C is 0. When C is 0, what happens is this entire term vanishes. So when C is 0, you're right. We are just minimizing half of W transpose W, which where the answer is we don't need to solve an optimization problem. We don't need a training set. The answer is 0. It turns out when W is 0 and you work through the whole math that we kind of worked at the beginning of the SVM unit, it corresponds to an infinite margin. So it gives you the maximum margin. It essentially says when C is 0, I don't care about the training set. Ignore this term, throw away the training set, maximize the margin as much as you can. And it gives you fantastic generalization at the cost of really lousy performance, um, which seems like a counterintuitive thing. What it does is essentially, this is it gives you a classifier that ignores the training set, and this gives you underfitting. This is a version of underfitting where the classifier can't even explain the training set correctly. So the training error is going to be really large. So let's write this down. C equals 0 implies bad training error. Let's consider the other extreme. When C is infinity. When C is infinity, when this goes to infinity, that says, let's think about how an optimizer can solve this problem. We want to minimize over all weights a function that includes an infinity. The only way in which this optimization problem even makes sense is if this second term, the hinge loss, the empirical loss, is somehow forced to be 0. If the hinge loss is somehow forced to be 0, then you get this indeterminate form 0 times infinity. There's at least hope that the optimization problem is meaningful. In other words, the only hope for solving this problem when C is infinity is if you force the hinge loss or the empirical loss to be 0. What does it mean to force the empirical loss to be 0? You want to find a weight vector that forces every single training example to be classified correctly. Let's think about what that means. If every single training example is classified correctly, you get 0 training error, but we are essentially ignoring this term. We are ignoring the margin term, which means that if the data set is, first of all, if the data set is not separable, if C is infinity, this optimization problem crashes. Let's assume the data set is separable. If C is infinity, that means you might end up overfitting the data. So let's, when C is infinity implies overfitting. So this is the extremes that we are trading off. On one hand, when C is, so let me draw the plot here, draw this thing. When C is 0, you get the regularization term dominates. And when C is infinity, the empirical loss term dominates. So here you get overfitting, where we force the training error to be 0. And here you get underfitting, where we ignore the training set and essentially live with a large training error with happy in the knowledge that our margin is infinity. Both these scenarios are actually bad. What we want is a sweet spot. And of course, C is negative does not even make sense, because that means that every time this loss is high, we gain points. So that doesn't make sense. So C is always going to be positive. So what this means is we want to find a sweet spot somewhere in between. We don't know where. For a C that controls the trade-off between a large margin, which is high generalization, and a small hinge loss, which prevents underfitting. So we want the best of both worlds. What's a good C? I don't know. This is a term that this is a value that you need to find by cross-validation. Usually, in practice, I've observed that for cross-validating for the C, you can just go in terms of orders of magnitude. So for instance, you can check for C inside the set, say, I'm going to just write so let's say you have 10, 1, 1/10, 1 by 100, and so on. Just the order of magnitude tends to be enough, or you can do something like 2 power minus 5, 2 power minus 4, and so on. On these, as the power gets larger, you are getting closer to the overfitting side. As this gets smaller, you're getting closer to the underfitting side. Somewhere in the middle is the sweet spot. And you just do cross-validation over all these values to find a C that is good enough. Are there any questions? How do you overfit with just one line? Imagine what you get is something, imagine your data set looks something like this. So let's say you have an example that is, say, plus, plus, perfectly linearly separable. And then you get a plus here. If I want to overfit this data, then I would have to find a line that somehow goes in between these two things here. You would agree that that's a pretty lousy separator. A better separator would be somewhere here. Give up on this example, pay the hinge loss on that, and you might get a much larger margin. So this is how you overfit with just one line. Your data set is linearly separable, but there's a point that's clearly mislabeled. Other questions? How does W transpose W relate to the margin? The way it works is when we started building up the theory for support vector machines, remember that the margin is the norm of Y, or not the norm. So it's Y W transpose X divided by the norm of W. And among all the examples, imagine that this is a separable data set. Among all the examples of this kind, the smallest value of this is the margin. This was step one. In step two, what we did is, if I want to maximize the margin, I want to find among all W's, I want to find this quantity. The next thing that we did was, this is a rather tedious optimization problem. Let me change the problem by noticing that I can scale the W's up and down. So instead, set closest, let me get rid of this min point to have Y W transpose X equals 1. This means we get maximize over W 1 over norm of W such that Y W transpose X is greater than or equal to 1 for every example. That's exactly the same as minimizing over W the norm of W under that condition, or equivalently minimizing over W transpose W. So minimizing W transpose W is the same as minimizing the norm of W, which is the same as maximizing the 1 over the norm of W, all of these under this condition. If this condition is true, then the minimum thing would have a 1 in the numerator there. This is I'm essentially unrolling the steps that we did in the previous lecture. Is there a real theoretical difference between noisy data, that is an outlier plus in the previous example that we saw, and a data where the plus is not noise, but a genuine feature? I don't know, actually. I don't think of, it's hard to think of a theoretical difference. This boils down essentially to the kind of features that you have. If you have fantastic features, ideally that should not happen. But we have the features that we have. So it's possible that a point that's correctly labeled might end up being placed close to other points that look nothing like it in terms of the label. So it depends on the feature space that we are working on. So it's hard to think of a theoretical difference there. What kind of norm am I using? It's always the 2 norm, because we're talking about these distances here. And that's why we get W transpose W. So that's why this regularizer is called the L2 regularizer. If you use a different norm, instead of you can replace it with one norm of the weights, then you get then you can get L1 regularization. Expanding on Han's question, can you go over slide 46 again, where I explained the 3 cases? Slide 46. Ah, okay, good. Yeah. So this is good. So let me revisit this. So in fact, you know what, rather than using this picture, let me, yeah, it's going to be easier for me to use this picture. I was thinking I'll just draw this again. So um, let's consider what is the meaning, first of all, of y times w transpose x. Why, assuming that, let's think about, first of all, what is the distance of a point. L2 norm is the Euclidean norm, but let's think about what's the distance of a point from a line. The distance of a point from a line is this quantity here, for all examples. So we can now ask, what's the distance, let's say, of this point from the line? The distance of that, it's basically yw transpose x divided by the norm of w. The distance of every point from this line is going to be, this norm of w term is going to stay with us. So essentially, it's a scaling factor that applies to all the points, given that the line is fixed. So for the sake of simplicity, I'm not going to write this expression. So I'm going to just say this thing here is just yw transpose x. So now let's consider the three cases. First, let's consider the three cases by going over a few examples. So let's consider the example that I've just circled here first. Then let's consider this example second, then this one third, and this one fourth. So for example number one, yw transpose x is this expression here. It is positive because y, and so what, assuming that the line is going to be predicting plus on this side here, w transpose x is negative and y is also negative, so yw transpose x equals is greater than 0. So yw transpose x, so for point number one, you have yw transpose x is greater than 0. If it's not, in fact, it's not just greater than 0, we have already assumed by the definition of the margin that for the closest point, yw transpose x equals 1. So notice that this is more than 1 here. So it's not just greater than 0. It is, so let me write it this way. So you have yw transpose x is greater than 0. Is it greater than 1? And the loss. For point number one, it's greater than 0 because it's on the y and w transpose x have the same sign. Not only that, it's greater than 1 because it's beyond the margin, because the margin is defined by the value 1. So the loss in this case is 0, because if yw transpose x is greater than 1, that means 1 minus yw transpose x is greater than 0. The loss, just to remind you, is max of 0, 1 minus yw transpose x. So this case, for point number one, the loss is 0. Next, let's consider point number 2. By the way, John, interrupt me if this is too slow or too fast. For point number 2, what we have is this point here. The distance yw transpose x is this expression here. It is clearly greater than 0 because it's a positive example for which w transpose x is on the positive side of the hyperplane. Not only is it greater than 0, it's greater than 1 because the margin is defined by this point for which the value is 1. Again, the same situation, yw transpose x is 1 minus yw transpose x is greater than 0, so the loss is 0. Let's consider point number 3 now. For point number 3, let me erase everything that's not necessary because we'll need some space for that. For point number 3, what we have, I erased the point label also. For point number 3, we notice that this is w transpose x, and so we have w transpose x is greater than 0 and y equals -1. So y times w transpose x is negative. But the quantity to consider is, so first of all, there must be a penalty. So this is not true. Of course, this is also not true. But the quantity to consider is 1 minus yw transpose x. If YW transpose X is negative, this quantity is positive, and we are adding a 1, which is really this distance here. So this is 1, this is Y times, this is minus the negative value of Y times W transpose X. So this gap here is the penalty that we need to pay. So that's, this term here is positive, the whole thing. This term here is positive, so the penalty is 1 minus Y W transpose X. For the fourth point, which is here, what we have is W transpose X is positive, but Y is also positive. So I'm writing in the top right corner. The product is greater than 0, but 1, this distance here is 1. So 1 minus YW transpose X is really this gap here. I probably mislabeled the thing in the previous case. It's that gap there. So this is 1 minus YW transpose X. And that is clearly not, that's clearly greater than 0, because it's a term that is, because YW transpose X is more than, is a quantity that's positive. So that's, so YW transpose X is greater than 0, but it's not less than 1. So the loss is 1 minus YW transpose X. So these are the, really, there are only 3 cases, because these 2 are really the same case in terms of the second and the third columns. I hope this clarifies things. We have only 2 minutes. So there's a question. In case 3, is it correct to say that the loss is greater than or equal to 1? Yes, that's actually the correct. In any time the example is misclassified, the loss will be greater than 1. If the example is correctly classified, but within the margin, the loss is greater than 0, but less than 1. And that is illustrated in this picture here. So let me clear all the annotation, because what in using the examples that we saw so far, we had case 1 was here, case 2 was here, case 3 was somewhere here, and case 4 was somewhere here. So this, the loss would be less than 1, because this height is 1 here. This is 1 plus YW, 1 minus YW transpose X. This quantity here will be minus YW transpose X, which is exactly this thing here, and so on. So yes, Alex, you're right. How does the norm of W relate to this graphic? It doesn't directly relate to that graphic. It's abstracted away in a slightly different way. We are notice that all of these things were so the norm of W is ignored here. It doesn't show up in this graphic at all. So it's an orthogonal thing. All right. It turns out that I totally am behind my plans for today. The goal for today was to quickly, I don't know how I was thinking that I could do that, but quickly finish up this part about the Hinge loss, and then spend the entire lecture talking about how to actually optimize the Hinge loss. But this is an important concept, not just the Hinge loss, but this notion of loss. So I'm happy that we spent some time on this. Please do think about this a little longer, because this idea of regularized risk minimization, or sometimes it's also called regularized loss minimization, is a really important notion. So very briefly, to kind of revisit that idea, we want to we define a notion, a function of law called loss that penalizes mistakes, and the goal is to find a classifier that has as low a loss as possible. But simply minimizing the loss can lead to overfitting. So we have this other term in an optimization problem called regularization, or a regularizer, and the regularizer penalizes complexity. So on one hand, we want to penalize mistakes. So this is and here we penalize complexity. And the general principle of regularized risk minimization is we want to find the classifier, the least complex classifier that has very low loss. All right, we'll stop here. We'll pick up on Thursday, where hopefully we'll finish off SVM, and that will set us up nicely to kind of take things forward. Don't forget your homework. If you haven't started, now might be a good time to start. I have office hours in 15 minutes. And if you have any questions, let's pick it up there. All right, I'll see you there if you show up. Bye.